January 28, 2022. Welcome to the 11th lecture in Lattice Boltzmann methods. So today we continue with this advanced topic of multiple relaxation times, this time in 3 dimensions. And there are some important distinctions between 3-dimensional multiple relaxation time and 2-dimensional multiple relaxation time, which we are going to see. So the content is, we are looking at the grouping of the moments. So we have to define groups of moments with specific relaxation rates. We look at what rotational invariance has as consequences on these rates, and then we actually come to a problem in the MRT method, and I hope you bear with me after this lecture, because this idea is, of course, we look at the problems in order to solve them in a later lecture. So there is some original work on the multiple relaxation time methods that I show here. So it's multiple relaxation time Lattice Boltzmann methods in 3 dimensions by Deumier et al. It's, as you see, 20 years old. It discusses the methods with the lattices D3Q15 and D3Q19. There are also other lattices for MRT, but in this paper we have only these. And this paper, as you see, it's important. It has 1,951 citations when I checked, I think, yesterday or so. So this is a very important paper, and a lot of these citations are actually from me. So I'm citing this paper very often. Yet I have to say that almost everything in this paper is wrong. Yeah. I mean, it's not completely uncommon that papers that give you wrong information still introduce something extremely important, a very important idea that later has to be corrected. And we hopefully come to this, but we have to understand that this is not the Bible. Okay, so it's not the absolute truth. So, and therefore I am telling this the untold story of MRT. Actually, it's not completely untold because I told it before, but some people don't want to hear it. Okay, so the thing is, with MRT, compared to what we already know, the BGK, we want to use different relaxation rates for different moments, yeah, in order to gain more stability or gain some other advantage from this. For example, accuracy. And in order to do this, we have to identify the moments which we can relax with different rates, and for this we need some grouping, yeah, because you could say, okay, say the D3Q19 methods that would have 19 independent moments, but then you could say, so each of this moment can has its own rate. However, you will see that this doesn't make sense, that each of the moment has its own rate. Yeah, and in order to understand this, we start from our favorite lattice, which is not the D3Q19, but the tensor product lattice. So the tensor product lattice, the minimal tensor product lattice is the D3. Sorry. D3Q27 lattice. That is the one that has all permutations of I equal to 1 to 0 to 1, the speeds 1, 0, and -1 in all directions. Yeah, this gives 27. This is because 27 is 3 by the power of 3. Yeah. Okay, and the question for this lattice, as it would be for other lattices too, is how many independent relaxation rates can we specify under proper assumptions, and the proper assumptions are of course isotropy. So the model should be, sorry, how many independent relaxations can be identified under isotropic assumptions. So we want to solve the Navier-Stokes equation. The Navier-Stokes equation is an isotropic equation, meaning that it is invariant under rotation of the coordinate system. So our relaxation rates have to respect this, that when we rotate the coordinate system, the equation that we solve doesn't change. Yeah, this is the condition. And now we start with the grouping of our raw countable moments. And then we see that we have to make some adjustments to this. So we have, of course, the moment M00, M100, so this is the momentum, M01 and M001. So these moments are conserved. So this is mass and momentum, they are conserved, so there is no relaxation. Okay, so four of the moments that we have are gone. Then we have second order moments. Second order moments, for example, M10, and of course, from this guy we have 3 permutations. And all permutations should have the same relaxation rate, otherwise it's not isotropic. Yeah? And this is a hydrodynamic moment. So as a second order moment, this appears in the Navier-Stokes equation. And next we have to make an adjustment, which is actually not a raw countable moment, but we have to use M20 minus M02 and M200 minus M002. This is something that we already discussed in the two-dimensional case, where in the two-dimensional case we of course had only one of them. Yeah, so these guys are the hydrodynamic moments. And they have the relaxation rates omega, which we equal to omega bgk. So they need to have the relaxation rate that adjusts the viscosity in the BGK method. And then this is also something that we had last time already. We have this isotropic part. This is the sum of all second order moments. We also call this the trace of the second order moments, and this is the acoustic moment. So it's actually identified to be the pressure. So I call this omega P, and this is adjusting the bulk viscosity. So it's not the bulk viscosity itself, but it is related to the bulk viscosity. So this was the conserved, the hydrodynamic, and the acoustic moments. And with this, we have now that there has been 4 of these, 3 of this, and 2 of this, and 1 of this. So we are we already have 12 of our 27 independent moments. So there's apparently still things missing, and these are of course the ghost moments. So we have ghosts, and from the ghosts we have different groups. So the ghosts start at order 3, so they are third order moments. And from the third order moments we have a group A, that are the moments 1, M1, 2. And from this sort of thing we have 6 permutations. So you can permute the indices 1, 2, 0 in 6 different ways. I'm not writing all of them down. Then we have group 3b. This has only one moment. This is M1, M111. And this has only one permutation. So then we come to fourth order moments, of which we have a group A. And this is the moment M220, which has 3 permutations. And then we have the group 4B. The group 4B that looks like this, M211, and this again has 3 permutations. And then we have the fifth order moment. Fifth order moment looks like M221, and this again has 3 permutations. And then we have one more missing, that is the sixth order moment. This is M222, and this has only 1 permutation. Now, okay, these are the groups, and the question, so we could now say that each group has its own relaxation rate, but this is not quite correct, or at least we have to check this. So I have to ask whether each type, so each of these groups here, whether each type has its own relaxation rates. So there are actually arguments for having fewer relaxation rates, and there's actually arguments for having more relaxation rates. So there is one thing that we observed, or that at least we said without explaining it in too much detail, namely that in the second order moments can be split in hydrodynamic moments and into acoustic, in this one acoustic moment. Even though the moments M200 are all of one type. Yeah? So if this happens to the second order moments, we have to ask whether this also happens to the other moments. So the moments M2, 0, 0, 0, 2, 0, and M0, 0, 2, they are one type, yet we take different relaxation rates for them. So two rates, since this M200 plus M020, which we call the trace, because this guy is the only one that is isotropic. So isotropic always means invariant under rotation. And the others are not invariant under rotation. So now we have to understand what this means. What is the rotation of a moment? Or of moments. Okay, remember that a moment is defined by a function over the by an integral over velocities, yeah, velocities in and the distribution function, yeah, and we regard a discrete lattice discrete distribution function, for which we look now at the velocity. So the velocity of distribution, and our distribution, we specify it with these three indices giving the velocities in I direction, in x direction, in y direction, and in z direction. Okay, so how does the velocity look like? So the microscopic velocity. The microscopic velocity is related to the grid spacing divided by the speed of sound. So by the time step, sorry, the grid spacing divided by the time step. And this goes into our quantum numbers, the vector of the quantum numbers I, j, k. So this is the definition of the lattice speed, and this can also be rewritten as I, the unit vector in x direction, plus j, the unit vector in y direction, plus k, the unit vector in z direction, and this into delta x by delta t. Yeah, so this is the definition of our lattice velocity. So what is a rotation? What is a rotation? A rotation is defined by a matrix R, yeah, which we now say this is an arbitrary rotation in principle. And this will give us a new vector of quantum numbers, E rotated, J rotated, and K rotated, which we can compute as I times R into E plus, so this is a matrix vector product, J times R and Y plus K R and Ez. Yeah, so we multiply each of these unit vectors by the matrix, or we multiply the matrix by the unit vectors, and then we get the I and j and k in the rotated coordinate system. Yeah, and under this rotation, everything has to behave the same way. Okay, so how does this rotation matrix look like? The rotation matrix, because it's a rotation about an arbitrary angle and an arbitrary direction, is something very special, very general, but we can look at special rotation matrices, special rotations about some specific axis. Namely the x-axis and the y-axis, just as an example. So, I mean, these things, you can look them up in Wikipedia. Yeah, this is something very, very simple. So this is the rotation matrix around the x-axis by a given angle alpha would look like 1, 0, 0, 0 cosine of the angle alpha minus sine alpha, 0 sine alpha and cosine alpha. So this is the rotation matrix about x, and I give you another one. Cosine about the y-axis would be cosine alpha 0 sine alpha 0, 1, 0 minus sine alpha 0 cosine alpha. Okay, and the rotation around the z-axis would then be the same thing. So if we, for example, rotate our coordinate system about the x-axis, we call this now x, j, x, and k. X, this would simply be I times r x into ex plus j x into y ey plus k x into ez. So, okay, in principle, all of these are very simple mathematical operations, but they take, a lot of time to write them down and to simplify them. So, in the following, I will show you just assume that you can do this, and we look simply at the results. Yeah, I hope I didn't make too many mistakes. Just before I started the lecture, I noticed that in one of the calculations to come, I made a mistake, and I tried to correct this. So I hope this was the only mistake. Yeah, but you can also take this as an exercise to check whether everything I write here is correct. So let us start with understanding the isotropic second order method, the acoustic method, moment. Why is the acoustic moment isotropic? So the acoustic moment, let's define this as MP, is again the trace of the second order moment. So it's M200 plus M020 plus M002. And this is, of course, defined as I j, and k. And in our case, all of them go from -1 to 1. So this is how we have the sum over the moments. And this is the I square plus the j square plus the k square. Yeah, where I square comes from this guy, j square comes from this guy, and k square come from this guy. Yeah, and this goes into Fijk. So what happens to this where we do the rotation of the coordinate system? So what happens if we rotate the coordinate system? So now I'm not going through all the mathematics. You have to either believe me or you have to do this as an homework. Yeah, this is the way. This is the way we do the rotation. So we have to compute I. Yeah, we have I square. Or no, we have I r square plus JR square. So these are this is the rotated quantum numbers, and this is KR square. Yeah. So these are computed by rotating I and then taking the square of this, rotating J, and getting the square of this. And what we find out, if we actually do this and simplify everything, that this is exactly I square, J square plus K square. Yeah? So this simply stays the same under any rotation of the coordinate system, and it's even independent whether we rotate around around the x-axis or by any other axis. So okay, I now just claim that this can be shown, that this is the case, without actually showing it here. So I hope you believe me, or you try to show it yourself. So because this change of coordinate system leads to exactly the same definition of the moment, we know that MP is invariant, because this is what it means, invariant under rotation. Okay, so is there something special? I mean, the other ones could be invariant under rotation too. Let's look at the hydrodynamic moments. Or let's look at one hydrodynamic moment. M200 minus M020. Okay? So, how's this guy defined? So this would be on our lattice the sum over ijk going from -1 to 1. And from this guy we have here I square plus, no, not plus, minus j square, which comes from this guy. And this goes into Fijk. So if we now apply a special rotation, and the rotation that I'm choosing is a rotation about the z-axis, we have a rotation around z-axis, then we see that if we take this moment I z square minus j z square should be the same moment, and we apply the rotation for I and j and take I square minus j square. What comes out after some simplification is I square minus j square times cosine to alpha minus 4ij cosine alpha sine alpha. But I hope that this is now correct, because this was in my notes and was previously somehow incorrect. So I hope I repaired it now. Otherwise, you have to check it again. Yeah, so what we see is that the outcome of this now depends on alpha. And that's not all. It does not only depend on alpha, but there is something that actually looks like a different moment, namely ij. Yeah. Now, what is ij? Remember that we have a moment that is defined as being dependent on ij, namely m110 is ij and k equal to -1 to 1, and ij fij k. So what does this mean? This means that there is a specific alpha that would map the moment m200 minus m020 onto the moment m110. Yeah? So this is m200 minus m020 maps on m110 by rotation of, which would be alpha p a quarter p, and the interesting thing is that this applies to the moment, but it does not apply to the lattice, which is another problem that we sometimes have to deal with. Namely the lattice, so this is 45 degrees. Yeah, the lattice does not map onto itself after rotation of 45 degrees, but only after 90 degrees. Can see this. So of multiples of 90 degrees, so p half. Okay, let's look at this now. Say this is our lattice. And we rotate it by p half, so then it will map onto itself. Yeah. Now take the lattice again. And what happens if we rotate it by only by a quarter of p. What we will observe then is that we get something pretty similar. However, the length doesn't quite fit. So this is a bit longer here and a bit shorter in the other direction. So it does not match. So this matches, and this has no match. It's not completely irrelevant to have either. I mean, it's not completely isotropic under this sort of rotation. So now what we can see, so physically we would say that these two moments, m110 and m200 minus m020, they should be the same, but numerically they are not the same. Because there is this anisotropy of the lattice. So, because the question that we try to answer is whether they should have the same relaxation rate, and up to now we would say yes, in principle, yes. However, because there is an anisotropy of the lattice, it may actually be possible or necessary to relax them with different rates in order to use the one isotropy to cancel out the other anisotropy. But this is a very advanced topic. I just wanted to mention that there is this possibility. For us, this possibility now doesn't take is not important right now. Okay. That was about the hydrodynamic and the acoustic moment. Let's come to the ghost moments. Which we were actually interested in. So here again, we have some moments of similar kind, say m210 minus m012. So we could again take this difference of moments. So they would have here the even part in the same direction and the odd parts. Sorry, I'm very funny. The odd parts in the y direction. So the y index is odd, and the x and the z indices are even. Yeah. So we could combine them in this way, for example, and this would be the sum over ijk equal from minus 1 to 1, I square minus k square into now j, fij, and k. So what happens to this guy when we rotate it? Let's rotate this around the y-axis where we have the odd index. Then what is going to happen is that we have ij y square minus ky square into jy, and if I computed this correctly, this would give us I square k square j cosine to alpha minus 4 ijk cosine alpha sine alpha. Okay, so there are two things that we observe, namely that apparently this moment rotates on ijk, but what is more important now is where it does not rotate on. Yeah, there is no rotation maps M210 minus M012 onto M210 plus M012. So however we rotate this, this will not happen. Yeah, that this guy becomes this guy. So what does this mean? If M20 minus M012 does never become M210 plus M012, then even though they look like they all belong to the same group, yeah, because they're all permutations of each other, they actually form two different groups that can relax with different relaxation rates. Yeah? So these things allow us to use different rates. So this means we have to split up one of these groups into two groups. Yeah, the other observation, which we already made, is that for a continuous distribution function, so that would be one with infinite speeds, infinite number of speeds, yeah, not on a lattice. So under these conditions, this M210 minus M012 would belong in the same group as M111. This is the case because if we do this rotation of this guy here, we may end up with ijk for a specific alpha, meaning we can map the moments M210 minus M012 directly on M111. So, but this is not the case on the lattice. Because the rotation alpha would be not equal to n pi half, where n, of course, is an integer. Yeah, and this means that for discrete distributions, as we obviously have in the lattice Boltzmann methods, they belong in different groups. So in the D3Q27. So where does this leave us? This leaves us at having three different relaxation rates, or three independent. I mean, you can also take the same value here, but you're not forced to by isotropy arguments. So we have M210 plus M012. This has three permutations. And this would be omega, because it's a third order, the third order moments omega 3, and we call this omega 3 plus. Then we have M210 minus M012, to three permutations. And we assign relaxation rates omega 3 minus, and then we have the single one M111, and this we call omega 111 as their relaxation rate. So again, because this may be confusing, and I'm on record somewhere in my long history in science, that for saying that this moment and this moment should have the same relaxation rate, they should be physically the same. However, as we discovered, this is not the case for a discrete distribution. And the reason for this is that the discrete distribution is anisotropic anyway. Yeah, so what did I write here with? Relaxing, so the relaxing M210 minus M021 and M111 with different rates would be anisotropic in a system with infinite velocities, infinite number of velocities. So this sounds like you should not do it. However, in practice, because the lattice is already anisotropic, then it's sometimes possible, and this is actually done in practice, to use anisotropic relaxation rates to use anisotropic relaxation to compensate for the anisotropy of the lattice. So the basic idea here is that two things which are both anisotropic can cancel each other out so that in sum they become isotropic. Yeah? And because the third order moments on the lattice are already anisotropic, we can adjust the relaxation rates of these anisotropic moments in order to cancel this anisotropy. But this is a very advanced topic. I just wanted to mention that this is a possibility, and because this is a possibility, we allow different relaxation rates for these different moments. So let's come to the fourth order moments. There again we have something very similar. We have the sum of the moment m220 plus m202 plus m022. This is of course the sum over ijk from -1 to 1, and now from the first guy we have I squared j square plus I square k square plus j square k square f I j k. So this, of course, this corresponds with this here. This here corresponds with this, and this corresponds with this. So then this is again an isotropic guy, as we see from that we take an arbitrary rotation. So for arbitrary rotations, we observe that IR square JR square plus IR square KR square plus JR square KR square is exactly equal to I square J square plus I square K square plus J square K square, and so this is an isotropic moment. So it belongs in a different group from the other non-isotropic first order moments. So we have a rotation now about the x-axis of ix square jx square minus kx square. I hope you can identify to which moment this belongs. This is j square minus k square into cosine 2 alpha plus 2 I square jk sine 2 alpha. So this is what comes out, and this guy here obviously belongs to m220 minus m202, and we observe again that this does not map on m220 plus m202 plus m022. So they are independent of each other. They are different physical quantities. However, it maps on m211. How do we see that it maps on to m221? Well, we see that there is a specific alpha for which we get here j square I square j and k, which corresponds to the moment m2, 0, 0, and for which this cosine 2 alpha would disappear. I don't know that there's not supposed to be a minus here. This is a, I don't know how this came here. So if this guy is the cosine 2 alpha is 0, of course the first term drops out and we would map onto m2 to 1, 1. Yeah, namely by rotation of alpha equals 2 pi to 45 degrees about the x-axis. So again, this leaves us with 3 independent relaxation rates for first order moments, namely one for m2 to 0 plus m2 0 2 plus m0 2 2, and this we call omega 4, and then we have m2 to 0 minus m2 0 2, and this comes with 2 permutations. And this we call omega 4 minus, and then we have m2 1 1 together with 3 permutations. And this goes with omega 2 1 1. Okay, then we still have our higher moments, and for the higher moments we don't actually have so many of them. The higher ghosts, so for example the 5th order moment m2 2 2 1, yeah, so we don't have we only have 3 of them. So there's nothing to separate, so we get just omega 2 to 1, so there's only one rate for them, and there's only one 6th order moment, so this is clear, this can have only one relaxation rate, omega 2 to 2. Okay, so in total, if you count all of this, we end up with 10 relaxation rates. So we have 10 independent degrees of freedom for how we can design our relaxation rates. However, this is not all of it, yeah, because we can still use different combination of moments and actually relax them. But we will always have at most 10 different relaxation rates. So we just found this is the maximum of relaxation rates that we can have under isotropic assumptions. However, these are not the moments that are usually used. Instead, as we discussed already last time, instead of the countable moments or the countable isotropic moments, people introduced orthogonal moments. And this, of course, causes a lot of hardship. I mean, not taking the making moments orthogonal is relatively simple, but making moments orthogonal is kind of stupid, and therefore leads to some hardship in for these poor students who have to implement these things, because this causes all sorts of trouble. Okay, so I'm not a good advertiser here for this. So in this paper that I mentioned in the beginning of this lecture today, the MRT uses the so-called unweighted orthogonality. They don't call it unweighted orthogonality, but this is what it basically is. So as a reminder, what is unweighted orthogonality? If we have a moment m phi, then this would be the sum over ijk, yeah, for the specific lattice, into this over the phi ijk times this fijk. So this would be the definition of the moment, where this guy here is the kernel over which we take the moment. And suppose we have a second moment where this is phi, or psi ijk, then we would have a psi ijk into fijk. So this is the definition of two moments, and they would be orthogonal according to this definition if the sum over ijk phi ijk times psi ijk, if this sum is equal to 0, yeah, then they are orthogonal. Okay, so if you define things like this and you do this in 2 dimensions, what you find is that it has little effect in the 2D Navier-Stokes equation. So little effect means it is neither harmful nor does it help with anything. Yeah? It's just not doing anything other than if you would relax the countable moments itself. However, unfortunately, and this is something very important to understand about the Navier-Stokes equation, the Navier-Stokes equation in 3 dimensions is pretty different from the Navier-Stokes equation in 2 dimensions. And this also applies to the Lattice-Boltzmann method. Yeah? So even though the same thing in 2 dimensions doesn't do much, it has big effects, and actually it has big problems in 3 dimensions. And in order to understand this, we now look at an example simulation that was specifically designed to highlight this problem. Yeah. So, but it is because it's a little bit complicated, this thing. We actually start with the observation. Yeah, that you know that there is this problem. So this example that was specifically designed to highlight this problem is the so-called double shear wave experiment. It's a completely academic, yeah, example that has no relationship to nature actually. But we have an analytical solution for the Navier-Stokes equation for this thing, and we see that we do not get to this analytical solution with specific numerical methods. So this is why we have this. So the idea is to measure 3-dimensional accuracy. So it's important that I mean, only for a special case, of course. And we have an analytical solution of the Navier-Stokes equation in a periodic domain. So we're using periodic boundary conditions. Where we would have it for different sizes, but the size that we now use, we call this the size L times 1 delta x times 2/3 L. Yeah, so you see it's a relatively simple setup, and because there is only 1 delta x in one direction, it is pseudo two-dimensional. Yeah, but it probes something three-dimensional. Okay, so I said there's an analytical solution. I write the example together with the analytical solution. So we specify the velocity in x direction u as being 0. Then the velocity in y direction, which we call v, we specify as u0 L0 divided by L times sine 2 pi x divided by L times cosine. This is why it's called double shear wave, because it's sine times cosine. 4 pi set L. Now what you observe is that the velocity in y direction varies in x and in z direction. This is why we call this a shear wave. Yeah, and this guy will decay in time exponentially with the viscosity, with e by the power of minus the viscosity times the time, and something that is related to the size of the size of the wave, the wavelength. Yeah, so it's 2 pi by L square minus plus 4 pi by 3 L. I made here a mistake. There must be 3 here. Yeah. So now I'm running this square and I'm trying to closing this brackets. Okay, so this is the solution. So you specify this at time step 0. Then if you then the exponential function will disappear. So this is your initial condition, and we have a velocity in z direction which is also 0. So now what you do is you initialize. Then you run the simulation, then you measure the decay. So from the decay, so how much the wave decayed, you can determine what viscosity you actually have. So this means you find the numerical the numerical value of the viscosity from how much the wave has decayed, and then you compute the error, and we call this error the error in viscosity, error nu, of the residuum of nu, and this is nu, the one that we specified, and the one that we computed, and we divide this by the one that we specified. So, and this is then repeated for different resolutions. And of course, we hope in diffusive scaling. So, and we know already that we have a method that is supposed to be second order accurate. So we hope that if we double the resolution, we have only a quarter of the error. Yeah. Okay, now using the following setup for this experiment, we have the hydrodynamic moments, all relaxing with omega is equal to omega bgk. And we have all the ghost moments with omega g equal to 1. And now the question is, what happens? So what happens? Nothing happens. I have to do this again. Okay, so this is the result for these simulations, specifying different viscosities, and we look at different methods that are here. So for example, I mean, there are some methods that we have not yet discussed, so forget about them. We have the BGK, which is this blue one. Here we have BGK, and we have here we actually don't have the MRT. We don't have the MRT here for the lower viscosities, because the MRT crashed. So at the highest viscosity, we actually have MRT. We have MRT up here, but this MRT has a much larger error. Yeah, so I mean, the good news is they are all second order accurate, as you see. So they have the decay that we were expecting. But the MRT has a large error for this low viscosity, and it actually becomes unstable and disappears completely from the plots for the lower viscosities. Yeah, so these are the lower viscosities, and here the MRT disappears. So the observation, this is actually not what we wanted. The MRT is unstable, even for the cases where BGK was stable. And even though we used additional dissipation, so setting omega g equal to 1 uses additional dissipation. So adding dissipation should actually make things more stable. But in this case, this didn't work. Okay, other observation, all models second order convergent, as we hope they are. This means our this means our asymptotic analysis was probably correct, but the error in MRT for the cases where we actually see the error for the MRT is larger than for BGK. So this is not what we wanted. Yeah, so we went through all of this big exercise to make it more accurate and to make it more stable, and now we see it's less stable and less accurate. And now we try to use the last 15 minutes to understand why this is the case. And this is a bit complicated thing. We have to go back to the asymptotic analysis, which you find in lecture 6, of course. And we do this to second order. So the expansion to second order MABC to second order is MABC equilibrium to second order minus, here comes the relaxation of any particular moment, which I now specify as omega ABC, of course, minus 1/2 dxm a plus 1 BC 1 plus derivative in y direction, first order, a, b plus 1, c, plus derivative in z direction of m, first order, a, b, c plus 1. So this what comes out of the asymptotic expansion if we use countable moments. Yeah? And now we specify A as equal to 2, B as equal to 1, and C as equal to 1. And then we get M211 to second order. So this is a first order moment. M211 equilibrium, second order, minus, and now we have here the moment omega 211 minus the relaxation rate omega 211 minus 1/2, and this is dxm 311, so there would be an aliasing in this, of course, plus dy m221 first order plus dz m212 first order. Okay, now apparently we have to specify our equilibria. So the equilibrium of this M211 equilibrium to second order is the factorization M200 to 0, M010 to first order times M00001 to first order, and all of this normalized by M000. So problems with my screen, M00, and this of this 0 order and this square. And this simplifies to theta, first order of velocity v times the velocity w, w is the velocity in the z direction, times rho to 0 order. So M311 appears in this equation, so this is nothing else than M111 to first order, and to first order this guy is 0. Then we have M212 to first order. This would be theta square rho to 0 order times v to first order. And this now gives us the equation 11.1. 11.1 is that M211 to second order is equal to theta rho to 0 order v1 w1 minus 1 over omega 211 minus 1/2 theta square rho 0, and this is multiplied with dy w1 plus dz v1. Okay, so now this is what comes out here, and now we said that omega 211 is equal to omega g, and this we said this is 1. Okay, so how does this now compared to the hydrodynamic moment. Yeah, because we looked at the ghost and actually we said the ghost doesn't matter. So what's the things that matter are the hydrodynamic moments. Now the hydrodynamic moment M011 to second order is rho 0 V1 W1 minus 1 over omega. So now this is this omega of BGK, yeah. 1 over 2 theta rho 0, and this goes into the y, the derivative in y direction W1, W1, and this goes plus d sets V1. Okay, now what we observe is that these two moments basically give us the same equations, and that we can put the one into the other. So we see that theta rho 0 dy, so this is the derivatives that we have here. Put them on the other side, and this is equal to minus M011 to second order minus rho 0 V1 W first order, and this divided by 1 over omega minus 1/2. This we can put into 11.1, and what we see then is M211 to second order is equal to theta rho 0 V1 W1 minus, and after putting the one in the other, we get here the 1 over the, omega g minus 1/2. All of this divided by 1 over omega minus 1/2 times theta, and now we have eliminated all the derivatives in this equation. We only have the second order moment M02011 minus rho 0 V1 W1. Okay. So this would be the case for BGK and MRT. But now comes the difference between the BGK and the MRT. In BGK, omega g is equal to omega, which means in BGK that 1 over omega g minus 1/2 divided by 1 over omega minus 1/2, that would be 1. Yeah, and I showed this is the prefactor here. So what happens in BGK, in MRT? So in MRT, we want to have omega close to 2 in order to have a low viscosity. Yeah, for low viscosity, high Reynolds number, efficient simulation, we want to go omega closer to 2. And we said we specify omega as equal to 1. That means that there's 1 over omega minus 1/2 divided by 1 over omega minus 1/2. So this guy here, this goes to 0. This means that the entire thing goes to infinity. So, and this means that even though M211 is a ghost, yeah, it is a big, really big ghost. So we blow this guy up, yeah. So because this M211 is, so to speak, infinitely larger than M011, so the second order moment, which is given by the physics. Okay, so this is a big problem, and let me see, 4 minutes, but I hope I have a few more lines to discuss, so we finished this. So this was non-orthogonal. This was MRT without orthogonalization. So what happens if we use orthogonal moments? Yeah, specifying an orthogonal moment M211. So this, according to these papers that derived them, is 3 times M, the countable moment M211 minus 2 M011. You can calculate whether this is actually now orthogonal. I hope it is. I also checked it, so it should be. So now if we expand this moment and relax this moment, we have to do the expansion of this of the sum of these moments, of course. So now this is now the guy that we relax. And this goes into 3 theta square minus 2 theta dy w1 plus dz v1. And if we do the same thing as before, we see that this is M211 equilibrium 2 minus 2 M011 equilibrium 2 minus 1 over omega minus 1/2 divided by 1 over omega minus 1/2 into 3 theta minus 2. Yeah, this is equal to minus 1. So everything that changed here was actually the sign, and changing the sign is actually also the problem. So we still have a large ghost, but now this ghost is inverted. It has a different sign. Which also basically is the problem. So I have only 2 minutes, but I'm also not a lot to write, but I want to finish this briefly, asking whether there is a better way, and we'll continue this discussion in the next lecture. But I don't want to leave this now here with this disappointment here. So I introduce a new orthogonal moment, which I now call small n, 211. This we specify as M211 minus theta M011. Yeah, so if we do the asymptotic analysis of this guy, we get, of course, M211 equilibrium second order minus theta M011 equilibrium 2 minus 1 over omega minus 1/2, and here comes now theta square rho 0, and this minus, so I specified this relationship in such a way that back here these two things cancel out, so they will have again dy w1 plus dz v1. And because this here is obviously 0, yeah, this will disappear. But now we can also look at our original ghost M211 under this conditions, and we say this is M2 N2112 plus theta M0112, and this is M211 equilibrium 2 plus theta 1 over omega minus 1/2. And so this has the same, this now has the same relaxation rates as the second order moments, and this basically means now this ghost is small. So there is a possibility to make this ghost small, and actually with a more intelligent way to build an MRT method than the original way the MRT method was built in non-weighted orthogonal moments. We can actually make an MRT method that is both more accurate and more stable than the BGK, and of course the original MRT method. Okay, so we briefly came over time. I hope this is still acceptable for you. Thank you very much for listening, and I see you next week. Stay healthy, yeah, and if you catch the virus, don't catch it too severely.